In section 6.7, we're going to talk about graphing other trigonometric functions. So let's start with the tangent of x. And what we're just going to do is use our calculator in radian mode to determine the tangent of some radian measures between negative 3 pi over 2 and 3 pi over 2. So if you plug this into your calculator, the tangent of negative 3 pi over 2 gives you an error message, and it probably says divide by 0. The reason that happens is because the definition of tangent is sine over cosine, which isn't something we really have talked much about yet, but it'll come into play later on. So if you think about where negative 3 pi over 2 would be, if you graphed it on the coordinate plane, remember negative angles go this direction, so negative pi over 2, negative pi, this is where negative 3 pi over 2 is. This ordered pair is at 0, 1. Remember that the ordered pairs, where the terminal rates hit the unit circle, are cosine, sine. So if you do sine over cosine, you get 1 over 0. And what's 1 divided by 0? Well, it's undefined. So anytime your graphing calculator gives you an error message and it says divide by 0, that's because really what's happened is you've gotten 1 divided by 0, which is undefined. The tangent of negative 5 pi over 4 will give you negative 1. Tangent of negative pi will give you 0. Tangent of negative 3 pi over 4 will give you positive 1. And negative pi over 2 will again give you an error message. Negative pi over 4 gives you negative 1. 0 gives you 0. Pi over 4 gives you 1. And pi over 2 again gives you undefined. Notice a pattern yet? The answers are going to be negative 1, 0, 1, undefined. Now, on a graph, what does undefined mean? Well, undefined is going to give you an asymptote. Remember asymptotes? Asymptotes were those lines that graphs got closer and closer to, but they never really touched them. So let's see, pi over 4, negative pi over 2, 3 pi over 4, negative pi, negative 5 pi over 4, negative 3 pi over 2. All right, so that's how I'm going to graph this. I'm graphing it in quarter pies. I should probably get rid of this negative and put my 1 here, my negative 1 here. So this is how it graphs. Everywhere the graph was undefined is an asymptote. And the way that we would account for asymptotes on the coordinate plane was we would use a dashed line. This is what we did when we graphed rational functions. At negative pi, 0, and pi, the graph was at 0. At negative 5 pi over 4, we were at negative 1. And at negative 3 pi over 4, we were at positive 1. At negative pi over 4, we were at negative 1. And at pi over 4, we were at 1. At 3 pi over 4, we were at negative 1. And 5 pi over 4, we were at 1. Now, if you graph this in your calculator, see what the shape of the graph looks like. It looks like this. Notice that it's not a straight line. Sometimes people misconstrue this as a straight line. But this is what the graph of tangent looks like. So one of the things I want you to notice is that it has a repeating pattern, and the repeating pattern is this long. So the question is, how far is it from negative pi over 2 to pi over 2? Well, if it's 90 degrees this way and 90 degrees this way, isn't that 180 degrees? And 180 degrees in radians is 1 pi. This length here would also be 1 pi, as would this. So the period of tangent is a little bit different from the period of sine and cosine. It only takes 1 pi before its pattern repeats, as opposed to 2 pi. I want you to notice that all the, I did something wrong over here. erase this. This should be 3 pi over 2. All the pi's over 2, the graph has asymptotes. At all the integer pi's, the graph hits the x-axis. And then at pi over 4, 3 pi over 4, 5 pi over 4, it hits either 1 or negative 1. One of the other things that's different about the tangent graph is that it doesn't have a maximum or minimum because the graph goes up and down forever. The only two trig functions that have amplitude are sine and cosine. Now let's go back and talk about cotangent. Cotangent is the reciprocal of each of these numbers. So here's the question of the day. What's the reciprocal of undefined? Remember, undefined is 1 over 0. So the reciprocal is 0 over 1. Well, 0 divided by 1 is 0. The reciprocal of negative 1 is negative 1. The reciprocal of 0 is undefined. The reciprocal of 1 is 1. The reciprocal of undefined is 0. So notice that some of the numbers are in the same place. The 1, the negative 1, those are in the same place as tangent because the reciprocal of negative 1 and 1 is both the same number. But the reciprocal of 0 is undefined and the reciprocal of undefined is 0. So what it's doing is it's changing where the asymptotes are at. It'll also change something else when we go to graph this in a minute. All right, so there's our table. We're going to use the same tick marks we used here, except I'm going to go graph this again. So let's see, negative pi over 4, negative pi over 2, negative 3 pi over 4, negative pi, negative 5 pi over 4, negative 3 pi over 2. That's pi over 2, pi, 3 pi over 2. All right, so the asymptotes this time were at all the integer pi's. So negative pi, 0, and pi. So I'm going to put the asymptotes here. And then the reciprocal of undefined was 0. So every place that had an asymptote on the tangent graph will be a 0 on the cotangent graph. And then all the other pi's over 4 were in the same locations, 1 or negative 1. So pi over 4 was at 1, negative pi over 4 was at negative 1, 3 pi over 4 was at negative 1, negative 3 pi over 4 was at positive 1, negative 5 pi over 4 was at negative 1, and 5 pi over 4 was at 1. So the difference here is I want you to notice the graph is going down from left to right instead of up from left to right. The period is again 1 pi. And the graph has no maximum or minimum. In example 1, we want to find each value by referring to the graphs of the trigonometric functions. Yes, I realize you could probably do this on your calculator, but for the sake of argument, I'm going to go back and look at the graphs. So part A says find the tangent of 7 pi over 2. So here was my tangent graph, and I know that 7 pi over 2 is not on this graph, but it doesn't need to be. What's happening at every pi over 2? Well, there's an asymptote. So if every pi over 2 has an asymptote, then asymptote is what we call undefined. Now let's go do this again in part B, the cotangent of 3 pi over 2. Here was the graph of cotangent. Look at what's happening at every pi over 2. At every pi over 2, it hits the x-axis. Well, that's 0. So the cotangent of 3 pi over 2 must be 0. In order to go look at the graph of cosecant, we're going to refer back to the graph of sine. So this was 2 periods of the graph of sine. Remember that secant is 1 over, sine is 1 over the cosecant, and cosecant's 1 over sine. So in order to graph cosecant, we're going to take each of these ordered pairs and we're going to find the reciprocal of the y-coordinate. So, what's the reciprocal of 0? Well, the reciprocal of 0 is undefined. So every time this graph hits the x-axis, the cosecant graph is going to have an asymptote. What's the reciprocal of 1? Well, it's 1, so this ordered pair is going to be in the same place. What's the reciprocal of negative 1? Negative 1. So these dots will be in the same place. So this is what I want you to notice. I want you to notice that within those asymptotes is like a little parabola. Doesn't that look like a little parabola that opens down? What do you think the reciprocal of it looks like? I bet it looks like a parabola that opens up. So this, I bet, looks like a parabola that's going down. Parabola going up, parabola going down. So the graph of cosecant, I'll get rid of some of this. I know it looks a little sloppy. What I'm trying to do is I'm trying to get rid of the sine graph. The graph of cosecant is a bunch of parabolas that go up or down. I want you to notice that the graph has to go this far before it repeats its pattern. So it still has a period of 2 pi. But all the asymptotes are at all the integer pi's, and the graph fluctuates between 1 and negative 1 at the pi's over 2. The graph does not have an amplitude like sine does, because in order to have an amplitude you have to have a maximum and a minimum, and cosecant doesn't have a maximum or minimum because it goes up and down forever. We're going to do the same thing to find the graph of secant, which is the reciprocal of cosine. So here's the graph of cosine, 2 periods. Same thing. Remember that anywhere the graph hits the x-axis, that's an output or y value of 0. And what's the reciprocal of 0? The reciprocal of 0 is undefined. So on the secant graph, remember this is 1 over secant. There's my 1. 0's reciprocal will be undefined. So this is where all my asymptotes are. And then the reciprocal of 1 or negative 1 is just the same thing. So these dots will also be on the graph. Again, we have these little graphs that look like little parabolas that open up or down between the asymptotes. So this part of the graph must go down. This part of the graph must go up, because what do you think the reciprocal of facing down is? Well, it's probably facing up. So this is what the graph of secant looks like. So now I'm going to go and I'm trying to get rid of part of this. I know it will not look beautiful, but it gets rid of it. Okay, there we go. So the asymptotes are at all the pi's over 2. And as with cosine, the graph hits 1 at every even pi and negative 1 at every odd pi. But just like with cosecant, there's no maximum or minimum because the graph actually goes up and down forever. So there's no amplitude. So in example 2, we're going to use the graph of each of these new graphs to find the value of theta for which each equation is true. So when is the cosecant of theta equal to negative 1? So let's go back to the cosecant graph for a minute. The first place we notice that it's at 1 is here at pi over 2. And then it repeats itself every 2 pi because that's the period. So the way we write that answer is pi over 2 plus 2 pi n. Remember, n is just an integer. It says 1 period later, 2 periods later, 3 periods later. All right, let's do this again for secant theta equals 1. Oh, I looked at the wrong one, didn't I? I was supposed to be looking at -1. Let's try that again. Not 1. Wanted to look at -1, which was 3 pi over 2, and then it repeats itself every 2 pi n. Sorry about that. And then secant theta is equal to +1. So here's the secant graph. The first place that it's 1 is at 0, and then it repeats itself in 2 pi. So we write 0 plus 2 pi n. Or we can say that it happens at every even pi n. Either one of those will work, although this will probably be the easiest for you to do. In example 3, they want us to graph cosecant of 2 theta minus pi over 2 plus 1, but I'm going to give you a little bit different way than the way the book does it, because if you look at the problem, example 3 in the book, which is a similarly done problem, they have all kinds of colors on the graph, and it's hard to tell which one is actually the final graph. So this is what we're going to do. The first thing is, just a reminder, cosecant and secant and tangent and cotangent do not have amplitude. However, they do have period, vertical shift, and phase shift, just like our other functions. So, how do you find the period? Well, the period is 2 pi over k. What's k in this problem? Well, it's 2. So the period is 2 pi over 2, which is 1 pi. To find the phase shift, you set what's inside the parentheses equal to 0, and then you solve for theta. So you add pi over 2, and then you divide by 2, and you get pi over 4. And it's pi over 4 to the right. And then there's a vertical shift. The graph gets shifted up 1 unit, because that's what the vertical shift is. Now this is what we're going to do to graph one period. Let's go back to the phase shift. Remember when we were graphing sine and cosine functions that had a phase shift? We would graph it from the phase shift, to the phase shift plus the period. We're going to do the same thing here. So we're going to start at the phase shift, so that's where our first asymptote is going to go. And the end of our period is also at an asymptote. It's going to be at the phase shift plus the period. Well, what's the phase shift plus the period? 1/4 plus 1 is 5/4. So we're going to start at pi over 4, and we're going to end at 5 pi over 4. All right, so now let's go graph this. Remember, there are a couple things going on here that we need to account for. First of all, let's worry about the tick marks on the x-axis. We're starting at pi over 4, and we're ending at 5 pi over 4. So the asymptote in the middle is going to be the average of those two numbers. So 1/4 plus 5/4 is 6/4, which is 3/2, and 3/2 divided by 2 is 3 pi over 4. So now I'm going to put my asymptotes here. All right, that's where I'm going to graph my one period. Now remember that the graph, one of them goes up and one of them goes down. The one in here is going to go up and the one here is going to go down. But the question is, where is the vertex of each of those little parabolas? Well, normally on the cosecant graph, they are at either 1 or -1. But what happens if I make the vertical shift 1? That means that one of the vertices is going to be 1 above that, so it's going to be at 2. And the other one's going to be 1 below that, which is going to be at 0. Now all I have to do is figure out, well, what are those two tick marks? So they're the average. So the first one, the one where the vertex is at 2, is the average of 1/4 and 3/4. So 1/4 plus 3/4 is 4/4, which is pi. Pi divided by 2 is pi over 2. And then 3/4 plus 5/4 is 8/4, which is 2 pi divided by 2 is 1 pi. And there's the graph of one period of the cosecant graph. Let's do an example of an application problem. A security camera is located 8 feet to the left of the midpoint of a line drawn down the center of a driveway. Let D represent the distance along the line from its midpoint. If T is time in seconds and the camera points at the midpoint at T equals 0, then D equals 8 tangent pi over 50T models the point being scanned. Graph the equation D equals 8 tan pi over 50T for the values of T between negative 25 and positive 25. Let's go back and look at tangent for a second. This was the graph of tangent. And I notice that the graph normally is from negative pi over 2 to positive pi over 2. We're going to instead graph it from negative 25 to 25, where the number in the middle is 0. Well, this kind of makes sense because we're changing the period of the graph. What's the period of the graph? Well, remember I said that tangent and cotangent had a different period. Their period instead was 1 pi. So we would instead use 1 pi over k. Well, what's k? K is pi over 50. So pi divided by pi over 50 is 50. And I want you to notice the distance from negative 25 to 25 is 50. Alright, so we're going to make this negative 25. We're going to make this 25. That means these are my asymptotes. What does the graph look like? Well, smack dab in the middle, it's going to hit 0. And then at these two tick marks, it's going to hit, well, not 1 and negative 1, I guess. I know this is not an amplitude, but that is going to tell you that it hits at 8 and negative 8. But now I got to figure out what the heck those two tick marks between 0 and 25 are. Well, what's halfway between 0 and 25? It's 12.5. So this must be negative 12.5. And there's my graph. In part B, we want to find the location the camera is scanning after 15 seconds. That's pretty easy. All we're going to do is we're going to plug in 15 for T. Just remember the calculator has to be in radian mode. And you should get an answer around approximately 11, and distance was in feet. The last question is, what happens when T equals 25? Now, let me go back and draw a picture of what's happening here. So you have this driveway, right? And down the center of the driveway is a line, and it's smack dab between the two ends of the driveway. We have a security camera that's 8 feet to the left of the midpoint of that line going down the center of the driveway. So let's call this the midpoint. So we have this camera over here, and it's 8 feet away. So the camera is scanning, so it's going this way and it's going this way. It's just going back and forth scanning the driveway. So the question is, what happens when the time is at 25 seconds? Well, if the graph has asymptotes at 25 and negative 25, then the camera must be pointing this way at 25 seconds. Why? Because is it really seeing anything? No. The answer is that the camera's pointing parallel to the driveway. And it can't see anything, which is why there's an asymptote there. The camera is parallel to the driveway. The last thing that we're going to do is we're going to write an equation if I give you information about it. For secant and cosecant, this works similar to sine and cosine. The only difference is there's no amplitude. So the graph, or the equation, I should say, is either going to be secant or cosecant. In this case, it's secant because they told me. K theta minus C plus H. Since I'm only plugging in 3 things this time, there is one thing I know I can plug in, and that's the vertical shift. Since it's positive 3, I'm going to put a 3 there. Then I have to find K, just like I did with sine and cosine. So you're going to set 2 pi over K equal to the period. It's a proportion cross multiply, so I get 3 pi K is equal to 2 pi. And then I'm going to divide by 3 pi. And I get k is 2/3. So now I can get rid of k and put 2/3. And the last thing is, remember, we set c over k equal to the phase shift, which is why you had to find k first, because otherwise you couldn't do this problem. So we're going to replace k with 2/3, and again, it's a proportion, cross multiply. I get 2c is equal to 2 pi over 3. And 2 pi over 3 divided by 2 is 2 pi over 6, and 2 pi over 6 reduces to pi over 3. So now I'm going to go replace this with pi over 3, and I know which type of function it is, so this is our equation. The only thing I want to remind you about tangent and cotangent, the only difference is that the period is pi over k. All the other 4 trig functions use 2 pi over k. And that was graphing other trigonometric functions.